This is chapter 15, section 2, evolution in process. Evolution is a continuous process. By examining genotypic and phenotypic evidence in modern organisms, we can see evidence that evolution has occurred. By considering species in relation to one another, we can also detect definite patterns of evolution. A big part of what the evidence that we put together to look at the evolution of species is the fossil record. Fossil evidence shows a long history of life on Earth. The fossil record shows that forms of organisms appeared, lasted for long periods of time, and then disappeared, only to be followed by newer forms of life that also eventually disappeared. The history of life is one of constant change and a tremendous diversity of life forms. A fossil is the trace of a long-dead organism. It is found in layers of sedimentary rock, like you see here. It is formed when sediment is deposited by wind or water. Now, fossils only develop from hard body parts like teeth, bone, and shell. Over a long time, hard minerals replace the tissue of the organism. Nicholas Steno proposed what is called the law of superposition, which says that successive layers of rock or soil were deposited on top of one another by wind or water. The lowest stratum, remember stratum means layer, is the oldest, and the top stratum is the most recent. This allows us to determine relative age of fossils. So relative age, using Steno's law, we can say a given fossil is older or younger than another fossil, depending on where in the layers it is. So fossils that are in the lower layers are older than fossils that are in the upper layers. However, absolute age is determined by radiological evidence using radioactive dating. Now we can make inferences from the fossil record. For example, we can infer that different organisms lived at different times. We can infer different organisms lived at different times, and so the strata hold different kinds of fossils in successive layers. This allows us to literally kind of look back in time and follow the evolution of organisms by comparing them to fossils that we find in lower layers. We can also infer that today's organisms are different from the past. For example, trilobites are different than anything alive today. And you can see the trilobite fossils here in this layer. What is a trilobite, you might ask? This is a trilobite. I think the closest thing that we have today would maybe be a horseshoe crab, but they're not related at all, I think. And 3, we can infer that fossils found in adjacent layers are more like each other than fossils higher or lower. So the closer they are together in the strata, probably the more similar they are. The further apart you get, the more different they are. And of course, that's because organisms change over time. So the further away that they are, the more time has passed, which means the more they have changed. And 4, we can infer where and when organisms existed by comparing fossils from around the world. Each fossil provides evidence about the environment the organism existed in and therefore adapted to. This is one of the big reasons why we came to the idea of how the dinosaurs went extinct, is because we looked at the stratum in a specific layer around the world. And in all places where they looked, they found the element iridium in a specific layer. So basically, if I go back and just kind of show you a little bit. So if we have the rock layers here, so we've got dinos, no dinos. So basically they wanted to look at this layer, what happened in this layer, where underneath that layer, before whatever event occurred, you had dinosaurs, and then afterwards there were none, and that's where they found iridium. And iridium is not found on Earth. It's only found in meteorites and comets and things like that. So that's where we came up with the meteor impact theory, or the multiple meteor impact theory, on the disappearance of the dinosaurs. Okay, so a lot of times when you have very distinct species in the strata rather, you will find that there are many in-between species that are kind of in between the living species and the older fossils. We call these transitional species. These have features that are between those of hypothesized ancestors and later descendant species. For example, whales. Hello there. Scientists hypothesize that modern marine mammals, like whales, evolved from early mammals that walked on land. This means that there should be fossils that share characteristics of both ancient land-dwelling mammals and modern whales. Scientists have actually found several fossils that form a sequence of transitional forms. So let's have a look at what they talk about here. So we have modern, we're gonna go backwards. So we start with modern toothed whales. They have forelimbs that are flippers. They also have tiny, non-functioning hip bones at the rear of their bodies. Now, you will not find hip bones in fish because they have what's called a pelvic girdle that supports fins, but they don't actually have hip bones. Having hip bones implied that they have come from an animal that used to have hind legs. All right, so then we go back in time and we have the Dorudon. This genus of mammal lived in the oceans about 40 million years ago. It resembled a giant dolphin and propelled itself with its massive tail. It had forelimbs that were flippers and tiny hind limbs that could not have been used for walking or swimming. So here we actually have the remnants of tiny little hind legs that I don't know if it's in this section or the next section that talks about vestigial features, which are body structures that are in the process of being gotten rid of because they're no longer necessary. So even though they have these little tiny hind limbs, you can't use them for swimming or walking. So they're in the process. This is what you refer to as a transitional species when you have something like that. Go back in time a little bit more and we have Ambulocetus. This genus of mammal lived in coastal waters about 49 million years ago. It could swim by kicking its legs and using its tail for balance. It could also waddle on land with its short legs. So here we actually have like hind legs that are used for walking. And then finally, all the way in the back, Pakicetus. And I got to look because my video is covering that text there. Scientists think that whales evolved from land-dwelling animals. One of these ancestors may have belonged to the genus Pakicetus, which lived about 50 million years ago. The fossil of Pakicetid is shown here. So then that's when you see that would be the ancestor of the modern toothed whale, which is a land-dwelling mammal. Because remember, life evolved in the ocean. So from single cellular organisms evolved into colonial organisms, evolved into, let's say for animals, you would have the fish and then amphibians, reptiles, birds, and then finally mammals. By the time you get to mammals, life had already evolved on land. Okay, another tool that we can use in trying to put together the evolutionary history of organisms is something called biogeography. So just put together geography and bio, the geographical distribution of fossils and living organisms. So here I've got a modern day armadillo. You don't have those in Thailand, but they are in the southwestern United States and I believe South America as well. Excuse me. And you find, when you look at the fossil record, in the areas where you find modern day armadillos, you find an extinct organism called the glyptodont, which looks amazingly like an armadillo. So that's where it's like, same thing with kangaroos. Kangaroos only exist in Australia, except for the red kangaroo, I think is in Asia somewhere, but it doesn't look like an actual kangaroo. It looks more like a bear, kind of like a small bear. Anyway, so you look at fossils that exist where current day animals exist, and then you find that they've evolved from previous species. Living organisms in the same area as extinct species look similar, like the armadillo and the glyptodont, which means they probably descended from old species. Like I said, all of these things are just kind of different tools that you put together to form a picture of how a species evolved. Okay, and now we have anatomy and embryology. Remember, part of Darwin's theory is descent with modification that predicts findings of anatomy and embryology. So if we look at the diagram here, you can see between a human, a penguin, an alligator, and a bat. The human and the bat are mammals, a penguin is a bird, and an alligator, of course, is a reptile. But you can see how you have the humerus, the radius, the ulna, the carpals, metacarpals, and phalanges, which we learned about last year, and how they have evolved in all of these species. These forelimbs are used in different ways in each animal, and yet they still are comprised of the same bones. They have similar bone structure, which indicates a common ancestor, even though they have different functions. You can still find anatomical similarities between them.